Okay. So if I'm going between atoms, you guys know how to go between atoms and molecules. You know how to go between, not atoms and molecules, between moles and molecules. You know how to go between moles and volume at standard temperature and pressure, as well as grams and moles. So next thing is, what if you want to figure out the number? Oh, and I think some of you already did a couple questions on here. The number of atoms. If you went past question 4 on the moles worksheet, you did this already a little bit. In a given number of molecules. So, for example, in copper sulfate, we're asking how many atoms are there in 5 molecules of this. I have got 1 copper, 1 sulfur, and 4 oxygens. And then I've got 10 hydrogens and 5 oxygens in every single molecule, right? Does that part make sense? So then what I'm asking is, how many atoms are there in 5 of that entire molecule? So if there's 5 of this whole thing, I'm going to have 5 coppers, 5 sulfurs. How many oxygens? 20 oxygens. I should add little plus signs in here so it just doesn't look like a huge number. Okay, how many hydrogens in 5? 50? 50? Awesome. And then how many oxygens? 25? Good. Okay, so we've got 25 plus 50, 85, 95. So we've got 105, right? 105 atoms in 5 of those molecules. Okay, does that make sense? Cool. Okay, so the steps that we're taking there, how many atoms are there in? So the first step is just to figure out how many atoms there are in one of these. So there's 21 atoms. Oh, sorry. There's 21 atoms in a copper sulfate because 1 of those, 1 of those, 4 of those, 10 of those, 5 of those. So there's 21 atoms in copper sulfate pentahydrate. In this molecule. So this is another unitary rate. So just like 22.4 liters for every 1 mole, this is a different unitary rate that we can use. And we can use it to convert between atoms and molecules. Okay, so therefore, moving forward, we've got 105 atoms in 5 molecules of copper sulfate pentahydrate. And we can just do that by figuring out the number of atoms in 1 and then multiplying it by however many molecules we have of that thing. All right, so how many oxygen atoms are there in 3.01 times 10 to the 23 molecules of carbon dioxide? Okay, so this one's a little bit trickier. Last time we only had 5 molecules, right? But here, this is a more realistic number. Molecules, we're working with huge numbers, right? So we want to know how many oxygen atoms are there in here. So what we do know is 3.01 times 10 to the 23 molecules. Oh man, sorry about that. There we go. 3.01 times 10 to the 23 molecules of CO2. And then what I'm going to do is set up a conversion ratio. So what we're going to do is times For every 1 molecule of CO2, I have got how many oxygens? 2 oxygens. So I've put my molecule of CO2 on the bottom, so that's canceling out. And I'm going to be left with oxygen when I do this conversion. So if I'm multiplying 3.01 times 10 to the 23 by 2, what I'm going to end up with is 6.02 times 10 to the 23 oxygens. So that's how many oxygens there are in 3.01 times 10 to the 23 molecules of carbon dioxide. Does that make sense? Okay, check out page 85 and try number 21, and then we're gonna come back and move on to the next page here. All right. So the next question is how many oxygen atoms are in 0.75 moles of carbon dioxide? So what we have is 0.75 moles of CO2. What we're looking for is oxygen atoms. And another thing that we know is that there's 2 oxygens for every 1 CO2 molecule, right? Okay, so this one's a little bit trickier than the last one though, because we're not actually given the number of molecules. We're given the number of moles. So we also need to know here that I didn't really leave enough space for this, but we also need to know that there's 6.022 times 10 to the 23 molecules in every 1 mole, right? So we're going to have to do multiple conversions here. So this is just like, do you all remember back in the math for chemistry section where there was that question that was like, if somebody wants to go from a gift to a horse and it's like 2 horses per chicken and like 3 chickens per goat, it's like that. So we're going to do multiple different units that we have to go through here. So it's not just going to be straightforward like the last couple were. All right, so we're just going to set this up as a series of fractions that cancel things out. So I'm going to start off with this 0.75 moles of CO2. And then it does not matter hugely what order we do this in, but let's just start off by getting from moles to molecules. So I've got 6.022 times 10 to the 23 molecules of CO2 for every 1 mole of CO2. So by doing this, I will cancel out 1 mole of CO2, or cancel out the mole of CO2 unit, and I'll be left with molecules of CO2. But it's not asking for molecules of CO2, it's asking for how many atoms of oxygen are in there. So now what I need to do is go, okay, I have got 2 oxygens for every 1 CO2 molecule. So then that's canceling out CO2 molecules, and I'm left with oxygen as my unit. So if I then go through this process and I go 0.75 times 6.022 times 10 to the 23 times 2, what I'm going to end up with is 9 times 10 to the 23 oxygens. So I've got that many oxygens in 0.75 moles of CO2. So this is just going multiple conversions, multiple things in a row. Did I lose anybody on this train of fractions? Okay, awesome. All right, so next one, how many oxygen atoms are in 3.01 times 10 to the 23 CO2 molecules. Okay, I want you all to try to set that up and do it. So I'll give you a couple minutes here. Try to set that up. Okay, so I'm just going to start writing this out. 3.01 times 10 to the 23 CO2 molecules. All right, what is the first thing? What's the first unitary rate that people multiplied this by in order to get towards the answer? 6 point. Okay, so what's that going to give me if I do that? If I do divide by that? Okay, that's all right. So, you know what? That might work. I'm going to go through it just like a slightly different way that makes sense in my head. But if you get to the same answer doing that, that's totally okay. All right, so you guys, what I'm going to do is I've got 3.01 times 10 to the 23 CO2 molecules. Okay, what I'm going to get into here is how many atoms, first of all, how many atoms of oxygen do I have in there? Hey guys, I'm talking over way too many people right now. Thank you. Okay, so I have got how many oxygens in every one CO2? Yep, 2 oxygens in every one CO2. So that is going to cancel out my CO2 molecules and give me how many oxygens I have. So then I've got the number of atoms of oxygen, if I just go from there. But it's asking me for how many moles of oxygen. So now I'm going to pull out that Avogadro's number. So I'm going to go, okay, 6.022 times 10 to the 23 atoms of oxygen in every 1 mole of oxygen. So if I do that, I've canceled out my oxygen atoms and I'm left with moles of oxygen. And if I do that math, I should actually have exactly 1 mole, I think. Yeah, 3 times 2 divided by that. Okay, awesome. So there's actually, 1.00 mole of oxygen. So sometimes it might take a little bit of like trial and error to figure out which order to put things in. Ellie, Paris, thank you. So it might take a little bit of trial and error to figure out like what order to put these things in. But as long as you're canceling things out and ending up with the right unit, just really keep track of your units. That's the big theme here. Keep track of your units, write down your units. So when we're doing multiple conversions, we can actually, oh, whoops. Oh no, that's okay. So we've got this nice little kind of flow chart thing here with moles in the middle. So this is kind of our central thing here, right? We've got moles, and to go to mass, we've got moles going to grams, which we looked at in 5.2. We can go from moles to atoms. We can go from moles to volume. We can go from moles to molecule. And then we can also go in between molecules and atoms. So these are all of the things that you should know how to do at this point. This conversion is from 5.1, from 5.1, from 5.1, 5.1, and then this is our new thing that we just did. So these are where you can find the notes on how to do those different conversions. But yeah, you guys need to be able to go like toggle between all of those different units. And you will never be asked to go between mass and volume directly. You can only get there by going through moles. So the only one that you don't have to go through moles to get to is atoms and molecules. Does that make sense? Okay, and this is on page 85 as well in your textbook. So you need to know the conversion factors that are involved in this. Okay, let's do this first example and then we'll take a break. So we're going to do how many atoms are in 26 grams of carbon. So this unit that we're looking at, hey guys, we're looking at grams to moles to atoms. So if we look back at that flow chart, it's asking how many atoms are there in 26 grams. Okay, well on my flow chart, I can go grams, and I'm looking at atoms over here. I've got to go through moles in the middle. So grams to moles to atoms. So then that's how I'm going to figure out how to set myself up. So I've got 26.0 grams of carbon. So now I've got to go to moles. So I'm going to go use molar mass, right? So carbon has a molar mass of 12 grams for every 1 mole. And then that's canceling out my grams. So now I'm left with moles. Awesome, good. But now I want to go to atoms. So I'm going to use Avogadro's number here. 6.022 times 10 to the 23 atoms of carbon for every 1 mole of carbon. And that's getting rid of my moles there. So now I'm left with atoms, which is what I'm asked for. So if I do that math, should end up with 1.30 times 10 to the 24 atoms of carbon. Okay. Any questions about how to set that up or why I did any of those steps the way I did? All right. So just when it's asking you for when it gives you something and it's asking you for something else, this flow chart is just super handy. Just be like, I've given volume, I'm asked for mass. Okay, I have to go gas, moles, mass. I'm given molecules and I'm asked for atoms. Oh, I don't have to go through moles. I can just go right here. So this flow chart is your friend. I will let you all take this into a test with you. So you can have this flow chart in a test if you'd like. Okay, so when we come back, we are going to do these 2 examples and then work on some questions on page 86. But you guys can have a break now. Let's do 15 minutes. So you can head outside if you want, or you can stay in here. But we're going to start up again in 15. All right. So this next example is asking us what the mass of this many molecules is. Okay, so if we look at our flow chart, in this case, we're starting with mass and we're being asked to go to molecules. So we have to pass through moles here. So what I'm going to write here is mass to moles to molecules. And then within each of these arrows, we use different conversions. So when we go from mass to moles, we use the molar mass of whatever our substance is, whatever our molecule is. And when we go from moles to molecules, we use Avogadro's number. So when we're going from mass of, molecules, oh my gosh, struggling here. Okay, 2.23 times 10 to the 10 molecules. I actually wrote this backwards. It should be molecules to moles to mass. My bad. Reverse those arrows. Or if you want to flip it around, that's cool too. Okay, so 2.23 times 10 to the 10 molecules. So I'm going to throw Avogadro's number in here, which is 6.022 times 10 to the 23 moles. Molecules in 1 mole. So should this 6.022 times 10 to the 23 be going on the bottom or the top of this next fraction here? Bottom, yes. 6.022 times 10 to the 23. because molecules per 1 mole. So we're wanting to cancel out the molecules, so that's exactly right. That should go on the bottom. Okay, and then I'm trying to go from this to mass. So now I have 1 mole of sodium carbonate, but what mass of sodium carbonate do I have? So in order to do that, we are going to need to know the molar mass of sodium carbonate. Okay, so if we get out a periodic table and add up 2 sodiums plus 1 carbon plus 3 oxygens, what do you all get for molar mass? Yeah, 106. Awesome. So we should end up with 106 grams per mole. So that's our missing piece of information here. So we're going to plug that in. 106 grams for every 1 mole. And that's canceled out moles. So now we're going to be left with grams, which is what we're looking for. So we just do the math here, and we end up with, hopefully, 3.93 times 10 to the negative 12 grams of sodium carbonate. So that's my end result, is grams. All right, next one, or I'll give you guys a second. Okay, this one is, what is the volume occupied by 50 grams of ammonium at STP, standard temperature and pressure? So what am I starting with and what am I going to? So if I'm looking for what's the volume occupied by 50 grams at STP, what am I starting with? Mass, awesome. And what's my end question? Volume, good. Do I have to go through moles? Yep. Whoops, that's not a mole. There we go. Moles to volume. Okay. Within that, there are a couple conversion factors. Mass to moles involves molar mass. Moles to volume is going to involve our STP number. 1 mole is 22.4 liters. All right, so let's set this up. I'm going to go 50 grams. And then I'm going to put a unit conversion here, which is going to end up being how many grams are in a mole. So my molar mass, grams per 1 mole. I need to figure out the molar mass of NH3. So if you look at your periodic table, anybody figure out what the molar mass of NH3 is? Do you say 18? 17, good. Okay, 17.0 grams per mole. So that's canceling out my grams. Okay, and then next thing is I'm going to volume. So I've got mole, yeah. Hey guys, I just can't hear what she's saying because I'm hearing you talking. Sorry, what was? Oh, in this? Yeah. So that's like really awesome that you picked up on that. When it's in a molecule, you can just have one of them. It's like if it's just carbon gas or just oxygen gas, you're right, they pair up. But when it's in a molecule like this, it's just however many it says it is. Yeah, but good application of that knowledge. All right. So 50 grams, 17 grams for every mole. And then the next thing I'm doing is I'm getting to volume. So 22.4 liters in every 1 mole. My moles need to go on the bottom, right? Because I'm trying to cancel out moles, get rid of them. So 22.4 liters is going on the top. And what I should end up with is 65.9 liters of NH3. Okay. So I think some of you already did this question, some of the 5 to 8 questions on that mole worksheet. If you haven't already, do those. Page 86, and then start on the many more mole calculation worksheet, which I'll just put up at the front here. Yeah, we're gonna, I think, do that for about, we'll see how long it takes. So I'll put this up at the front and then work on these questions, and we'll go over some of them if people are having a consistent hard time on the same ones. And I'll throw that up on the Google Classroom here as well. Yes, many more mole calculations, so I'll put that up on the table here.